Picture this. You want to send a letter, but all you've got is the recipient's name, no address. You need to track down where they actually live to deliver it. In the networking world, IP addresses are like those names. They identify devices at layer 3. Meanwhile, MAC addresses are used at layer 2, similar to mailing addresses. Before a host can send a data frame on a local network, it needs the MAC address of the recipient. That's where ARP, or Address Resolution Protocol, comes in. Think of ARP as sending out a shout in the neighborhood. Hey, who here has this IP address? It broadcasts the request, and the right device answers back with its MAC address. ARP is a fundamental protocol in networking, and trust me, it's something the CCNA exam loves to quiz you on. Host A wants to send a packet over to host B, who's lounging at 192.168.1.20. The first move for host A is to check its ARP cache. Imagine it flipping through a little black book to see if host B's MAC address is already jotted down there. If it's found an entry for 192.168.1.20, it just uses that MAC address to deliver the packet. But what if host A comes up empty-handed? That's when it sends out an ARP request. Who has 192.168.1.20? Tell. This request is broadcast to the MAC address FFFFFFFFF, which is like shouting across the neighborhood so everyone can hear it. Host B, recognizing its own IP like it's hearing its name called for dinner, sends back a unicast ARP reply. It quietly slips host A its MAC address. Now equipped with the details, host A updates its little black book, ARP cache, and finally sends the original packet off on its way. Every device maintains an ARP cache, which is like a guest list matching IP addresses to MAC addresses. If you're on a Cisco router, typing show IP ARP will give you the details. But don't get too attached to these entries. They tend to vanish after about 20 minutes. Now, gratuitous ARP is like someone walking into a party and loudly announcing their name and phone number without anyone asking. It's useful for catching IP conflicts and dealing with failovers. The downside? It's also a popular trick for ARP spoofing attacks. Let's dive into 4 little traps in the world of ARP. First up, ARP operates at layer 2, using MAC addresses for broadcasting. But here's the catch. It's actually all about IP addresses inside the message to figure out who it needs to chat with. Yes, it's a bit like a magic trick, showing you one thing while doing another. Next, ARP is a bit of a homebody. It only works within the same subnet. If you need to communicate across subnets, your device will send an ARP to the default gateway for its MAC address, not directly to the distant destination. Think of it like sending a letter to your friend's house via the local post office first. You let them handle the routing. Third on the list is proxy ARP. This is like having a router play a sneaky game of post office helper. It answers ARP requests for devices on another subnet, which is handy, but can also hide configuration errors you might not be aware of. And lastly, there's gratuitous ARP. It's like a wake-up call for the network. Used by protocols like HSRP, VRRP, and GLBP during failover, it announces the change of the active router, updating the MAC tables faster than you can say, network hiccup. So there you have it, your ARP traps all laid out, ready to trip you up if you're not careful. That's ARP wrapped up for you. The request-reply shuffle, those helpful ARP tables, and a touch on gratuitous ARP. It's the bridge between layer 3 and layer 2 that keeps things running smoothly. If you're ready to test your knowledge, head over to Courseiva.com for some CCNA practice questions. Keep pushing forward, you're doing fantastic.